Hello and good morning. Today we're going to start talking about section 5.4 entitled Parameters for Binomial Distribution. Let's start out with a little bit of an example here. Let's say we're in a region of the world where the probability of a male birth, in other words, probability of a boy, is 0.7 in any one birth. Kind of unrealistic assumption. I'm going to let x equal the number of boys in 4 births. So we see x is a random variable, a discrete random variable. If I successively apply my binomial probability formula, we can find the probability for all possible number of boys in 4 births. Well, in other words, I can find the probability of 0 boys, the probability of 1 boy, well, all the way up to 4 boys. We can have a minimum of 0 boys and a maximum of 4 boys, right? Alright, so I'm going to successfully apply my binom PDF operator on our calculator. Well, if I've got n trials, that's 4 trials here. The probability, if I'm calling a boy a success, the probability of boy is then 0.7, and I'm looking for 0 successes, and I punch this out on my calculator, and I get 0.0081. Alright, I'm going to do this for all possible values of x in this binomial experiment. Well, for the one case, well, really I just recall my previous line of code, and I substitute in 1 for 0, and let the calculator do the hard stuff, and leave the interpretation up to us. Alright, I won't write out the code for the next 3 cases. Again, using the binom PDF command for the proper choice of x number of successes, I get the resulting values. Alright. What I'm going to do now is summarize these results in a table. Really, I'm constructing a binomial probability distribution for this binomial experiment. So what I'll do, let's go down here, I'll summarize the above results in a table fashion. Well, do it like this. Do the best I can freehand here. Alright, remember x is the number of boys in 4 births, so x can take on 5 possible values from 0 all the way to 4. And let me take a minute to copy these down again. Alright, so what I have done here, I have constructed the probability distribution in table type fashion for a binomial experiment. Recall the criteria for binomial experiment. You've got 2 outcomes per trial, a fixed number of trials, and the probabilities are all independent in any given trial. All right, so I call this, well, I'll say this is, well, the first thing it is, it's a probability distribution. But it's a special type of probability distribution. It's a binomial probability distribution because it's based on a binomial experiment. Write that down. because it's based on a binomial experiment. Okay? Binomial distributions, they look a lot like other probability distributions. They're almost impossible to tell by looking at a table of values like this whether it's binomial or not. Oh, please be aware of that. Once I've got a probability distribution, as in our last section, we might want to consider what is the mean and what is the standard deviation of a probability distribution. You may recall formulas for the mean of a probability distribution. Well, the mean is kind of easy, summation x times p of x, and the standard deviation is, well, it's kind of nastier, summation square root of summation x squared times p of x minus mu squared. You'll recall those formulas from section 5.2. Alright, it turns out in a binomial situation, these two formulas can be greatly simplified, and I'm going to give them to you right here. But you have to remember to use these only in the binomial case, in the binomial distribution case. Let me write them down. For a binomial probability distribution, two outcomes per trial, fixed number of trials, independent trials, etc. The mean can be very simplified by this formula, mu equals np, which is much simpler than summation x times p of x in the general case, and sigma equals root npq. Right, so these are certainly much easier formulas to memorize and deal with. Well, the trouble is students sometimes try to use them when they shouldn't be used. Again, this is for the binomial probability distribution case only. Well, let's see. Let's look at an example. I'm looking at example 1 on page 223. Let me turn there myself. We'll read it together. Example 1, page 223. Alright, the brand name McDonald's has a 95% recognition rate, etc. A special focus group consists of 12 randomly selected adults to be used for extensive market testing. Right away I know my N is going to be 12. For such random groups of 12 people, find the mean and standard deviation for the number of people who recognize the brand name of McDonald's. Alright, well, we want the mean and standard deviation for the number of people that recognize McDonald's in a group of 12. Well, the probability of success then is the probability of recognizing McDonald's. That's going to be 0.95. So the mean, this is a binomial probability case, right? We've got a fixed number of trials, 2 outcomes per trial. Either you recognize McDonald's or you don't. The probabilities are implied to be independent in all of these trials, so we're going to assume a binomial experiment here. And then mu equals n times p. Well, n, of course, is 12. P is 0.95. And if I punch that out, I get 11.4. And notice that mean is kind of near a maximum value of 12, which is what you might expect when you're talking about recognizing McDonald's, or in the number of people in 12 that recognize McDonald's. Probably pretty close to 12. Alright, so much easier than grinding out a table and doing summation x times p of x, I think you'll agree. Let's look at the standard deviation. Again, in a binomial experiment, sigma SD equals root npq. Well, we know n, we know p. What we don't know is q, but of course we know q. The probability of failure is always 1 minus p in any trial, and of course in this case it's 0.05. So sigma then is root 12 times 0.95 times 0.05. And I punch this out on my calculator, I get 0.75. Alright, so that finishes example 1. Much easier formulas to deal with. Mu equals NP and sigma equals root NPQ, but again, only in a binomial probability distribution. Let's look at example 2. On page 224. Again, deals with the same given information about McDonald's. From example 1, we see that groups of 12 randomly selected people, the mean number of people who recognize the brand name of McDonald's is 11.4, and the standard deviation is sigma equals 0.8. All right, they've rounded that off, and let's embrace the book's value. So mu equals 11.4, and sigma equals, all right, we'll say 0.8, and they've rounded to 1 decimal place. I tried to not make a big deal about rounding rules, as you know. Let's look at part A. For groups of 12 randomly selected people, use the range rule of thumb to find the minimum usual number and the maximum usual number of people who recognize the brand name of McDonald's. Well, the range rule of thumb says this: if you're more than 2 standard deviations away from the mean, you're unusual. Alright, what that means, I'm going to create milestones here. One of them 2 SDs above the mean, one of them 2 SDs below the mean, to establish my boundaries of usualness. Alright, so mu minus sigma, well, mu is 11.4. Sigma, the book says, is 0.8. Alright, so on the low end, we've got 13. On the high end, well, I'll take 11.4, our mean, plus 2 times 0.8. And I punch this out, and I get, let's see, oh, I got them mixed up here, hang on a minute. Mu plus 2 sigma is 13 people, sorry. Please make this correction. And mu minus 2 sigma, let me check it, 11.4 minus 2 times 0.8. Alright, we'll call it 9.8 people. So if my number of people that recognize McDonald's in 12 falls within this range, I say those results are usual. And beyond those milestones, I claim those extreme values are unusual. Okay? Alright, so the book asks us in part B, in one particular randomly selected group of 12, is 12 an unusually high number of people who recognize the brand name? So out of 12, is it unusual? Is 12 an unusual number of people to recognize McDonald's? Well, according to these milestones, clearly not. 12 falls short of that unusual range, so I'll say not unusual. That would be my answer to part B. Okay? Let's do example 3 now on page 224, and this will be the last example. It has 3 parts to it, somewhat similar. This example on page 224 cites the chapter problem. Remember, the chapter problem is kind of a motivational problem given at the beginning, at the very beginning of each section in the book. It talks about an XOR, a method of gender selection. Let me read example 3 for you. You might want to turn there to your books. The chapter problem includes results from the X-sort method of gender selection. Assuming 945 births, there were 879 girls born to parents using the X-sort method. All right. Assuming that boys and girls are equally likely, use formula 5, 6, and 5, 8, those are binomial probability formulas, to find the mean and standard deviation for the numbers of girls born in groups of 945 babies, as in the chapter problems. All right. So let's see. Let me write some things down here. We've got 945 births. All right. Out of those 945 births, we had 879 girls and 66 boys. Well, it looks like this X-sort method is having some success, at least if you call having a girl a success. Alright, assuming boys and girls are equally likely. This is part A. Alright. Use these simplified formulas for the mean and standard deviation for the number of girls born in groups of 945 babies. All right. So this is going to be a binomial experiment. You've got a fixed number of trials. Here it's 945 trials, 2 outcomes per trial. The probabilities of boy and girl in any one trial is constant, and all trials are independent, so I can claim a binomial experiment. So mu equals NP, so this is a breeze. It's going to be 945 times, well, what's P? Well, remember in part A they ask us, or they tell us, to assume that boys and girls are equally likely. Doesn't look like that in the results, but again, the book is telling us that assuming boys are equally likely, if I'm calling a girl a success, then the probability of a girl is going to be 0.5. Alright, so our mean in this case is going to be 945 times 0.5. That's going to be 472.5 in girls. This is the mean number of girls we might expect in this binomial experiment. Alright, oh, the standard deviation, I almost forgot. The standard deviation for number of girls is root NPQ. So it's going to be root 945 times P is 0.5. Well, what's Q? Well, if you know P is 0.5. Again, the probability of girl is 0.5. Q is going to be the probability of a boy. It's going to be the probability complement of 0.5, which is, of course, also 0.5. So remember, in a binomial experiment, P equals 1 minus Q and vice versa. Q equals 1 minus P. And I'll punch this out on my calculator, and I get a value of 15.4 in girls. That's my standard deviation for the number of girls born in this experiment, again with the assumption that boys and girls are equally likely. Okay? Alright, part B. Use the range rule of thumb to find the minimum usual number and the maximum usual number of girls born in groups of 945 births. Alright. Range rule of thumb talks about boundaries of usualness. And again, if you're more than 2 SDs away from the mean, high or low, you are in unusual range. So I claim anything in this range is usual. Mu, recall mu was 472.5. And minus 2 sigma on the low end. Sigma is 15.4. Alright, so my low ball value here is going to be 441.7. Kind of getting low on the screen here. Similarly, on the high end, I've got a mean of 472.5 plus 2 times sigma, 15.4, is going to be 503.3. So anything in this range, I'm going to, for my number of girls, I'm going to consider usual. Okay? So that's B. They wanted us to find the min usual and the max usual number of girls in these 945 births. Let's go to part C. I'm going to have to get a new screen. Give me a minute. Alright. So now part C. The chapter problem described the X-sort method of gender selection that resulted in 879 girls born in a group of 945 babies. Let me write that down again. 945 births. And they had 879 girls. Yikes. Seems like a lot of girls. If you're assuming boys and girls are equally likely. Well, let's see. They ask us then, is 879 girls unusually high? Well, let's see. Again, assuming boys and girls are equally likely, we had a minimum usual value of 441.7 for a number of girls and a maximum value of 503.3. Any number of girls in this range is usual. Anything beyond this middle range is unusual, and clearly 879 girls is way out in this unusual range, unusually high. Right? So I would say because the result of 879 girls falls above the range of usual values, we consider the result of 879 girls to be an unusually high number of girls. Okay, let me write that down with the assumption that boys and girls are equally likely. If you're assuming that, then 879 girls in 945 births is unusual. Some might say highly unusual. And this is suggesting that the X-sort method, whether it be a diet type of treatment or exercise or pills, who knows, injections, suggests that the X-sort method favors, maybe highly favors, girls in any birth. Okay? Alright, we'll call it a day. It's the 23-minute point, and this concludes section 5.4, parameters for binomial distribution.